Data centers pack tens of millions of dollars of critical hardware into dense, heavily cooled rows. When a thermal event occurs in these corridors, the facility has seconds to react. That response cannot rely on human hesitation or vague programming. This cause and effect matrix acts as the deterministic operating contract between detection systems and physical responses. The central core connects 5 nodes. It must detect inputs, verify legitimacy, command external systems, coordinate evacuate protocols, and prove the safe execution of commands through physical feedback. This authority pyramid shows how that contract is governed. Standard OEM equipment listings form the baseline, but local laws and the authority having jurisdiction, or AHJ, always sit at the top. Technical minimums are legally bound by those upper tiers, overriding any default factory setting. The matrix is the literal law of the building. If a scenario is missing from this contract, the system will not execute it. Ambiguity in these programming rows directly results in catastrophic hardware loss or life safety failure. To maintain the integrity of that matrix, the facility must physically and digitally isolate the systems that execute life safety commands from the systems used for general facility monitoring. This data flow architecture illustrates isolation. A red firewall separates the fire safety control layer from monitor-only interfaces like the building management system below. Lower-tier platforms receive supervised events for awareness, but hold absolutely zero undocumented authority to trigger life safety outputs, bypasses, or resets. This signal classification matrix enforces that rule, distinguishing an alarm condition from a supervisory condition. Supervisory signals reveal off-normal conditions, like closed valves, demanding urgent maintenance escalation. They do not, under any circumstances, cross the firewall to initiate unrelated life safety evacuations. By explicitly classifying inputs, the matrix ensures that a maintenance alert lacking life safety authority cannot cross the firewall and accidentally trigger a multi-million-dollar suppression dump. Data halls utilize massive volumes of forced air to keep servers cool. These high-velocity air currents drastically alter normal smoke behavior, preventing a thermal plume from rising neatly to the ceiling. This cross-section shows the physics of airflow dilution. High-velocity supply air, marked in blue, transports and heavily dilutes the smoke. Because the smoke is so scattered, traditional area spot detectors are entirely inadequate for early warning. Instead, detection must map perfectly to the physical airflow paths of the specific room. Aspirating smoke detectors continuously sample the air by drawing it from underfloor supply paths and high-velocity return air plenums. This staging ladder breaks down how those aspirating smoke detectors, or ASDs, classify the diluted smoke. The system climbs through 4 tiers, moving from a very early alert monitor state up to a Fire 2 verified true alarm. Because of severe dilution, the early alert and action states are strictly technical investigation states. They prompt personnel to inspect the zone, but they are not evacuation triggers. The design rule is uncompromising. A low ASD threshold can never be used as a suppression release input unless the approved hazard analysis explicitly requires it. A facility's detection strategy cannot rely on default device sensitivities out of the box. It must be engineered to match the exact thermal and velocity physics of the protected space. This timeline outlines the program clock. Once the panel accepts an initial input at T0, it does not instantly dump suppression. It starts a strictly governed escalation of time. For a staged alarm, an investigation clock begins. If the technical staff cannot resolve the issue before T1 expires, the matrix executes Stage 1 notifications. If the escalation clock reaches T2, the system automatically triggers Stage 2 evacuation outputs. This logic flowchart contrasts that yellow staged pathway with the red true alarm pathway. A true alarm relies on high-confidence inputs, like 2 detectors tripping in a cross-zone setup or a manual call point activation. When the panel receives a verified confirming event, it instantly bypasses all optional stage timers. It validates the rule, commands the notification, and executes the full event row immediately. This pseudocode block shows how the matrix structures this logic as a rigid state machine. Using strict if-then coding principles eliminates ambiguous timers and undocumented interactions from the system. Time is a highly controlled variable within the logic core. The timers give on-site personnel a designated window to investigate a localized fault without ever compromising the definitive point of no return for life safety. Once the digital state machine confirms an event, it has to physically actuate the suppression hardware. In a data center, releasing water or gas requires absolute certainty. This piping schematic details a double interlock preaction architecture. The pipes above the servers are filled with pressurized nitrogen, marked in green, holding back the pressurized water supply, marked in blue. To release water, two independent blocks must be satisfied. Block 1 requires an electrical smoke detection criterion to be met. Block 2 requires the heat of a fire to physically break a pneumatic sprinkler bulb, dropping the nitrogen pressure. Block 3 dictates that the mechanical preaction valve opens only when both the electrical and pneumatic steps are satisfied. If a pipe is accidentally hit by a ladder, the nitrogen drops, but without smoke detection, no water enters the piping. For gas suppression, this circular diagram breaks down the four-quadrant clean agent release sequence. It moves systematically from the initial local alarm in Phase 1 through verification to physical actuation in Phase 4. During Phase 2, the verified cross-zone criterion starts the pre-discharge countdown. Critically, this phase isolates the HVAC and dampers to seal the room. Phase 3 activates the warnings, and abort stations can pause the release, but only according to their strict equipment listing. The physical suppression hardware remains firmly locked in a safe state until the digital state machine provides absolute dual-factor verification that a fire actually exists. This HVAC philosophy chart details how the matrix commands cooling systems during an event. Data centers explicitly reject the traditional default of shutting all air units off during a fire alarm. The business continuity rule demands that while the affected zone isolates to prevent smoke spread, unaffected data halls must remain operating. Maintaining critical cooling in those adjacent zones prevents massive secondary equipment loss. This building cross-section shows the active smoke control pressure strategy. The matrix turns on extraction fans to create a negative pressure goal on the red fire floor, while commanding supply air to positively pressurize the blue adjacent zones, containing the smoke. This interlocks table shows how the matrix simultaneously commands security barriers. Different barriers require entirely different fail states based on their function. Egress doors and electromagnetic locks prioritize human escape, dropping power for a fail-safe free egress. Perimeter responder gates, however, follow a separate fire brigade access plan. They do not share the same fail state, and the matrix must command them independently. The matrix is a master orchestrator. It executes a complex balancing act, prioritizing the immediate demands of human escape while executing targeted commands to ensure the survival of the surrounding critical infrastructure. This flow diagram maps the testing evidence chain. Software testing of panel logic at the factory is necessary, but it is meaningless without real-world physical integration testing at the facility. The matrix must pass specific integrated system test, or IST, scenarios. These colored blocks outline tests for data hall smoke escalation, clean agent logic aborts, and critically, contingency responses to physical fan failures. This event chronology log establishes the strict rules for those tests. Before an IST begins, every fire cannel, server, laptop, and witness camera must be synchronized to one common time source. This timing analysis chart shows the equation for end-to-end proof. Total protected time equals detection, confirmation, routing, and discharge. Here, command issues at 1.2 seconds, but required field proof, the physical damper closing, takes 24 seconds. It passes, falling under the 30-second limit. A digital event log exported from a fire panel is insufficient proof of protection. Only validated physical field feedback proves the contract has been successfully executed. This interface table addresses high-risk electrical spaces requiring distinct logic. Lithium-ion battery and generator packages present unique thermal challenges. The advanced rule applies. Main fire alarms coordinate emergency states, but local best controllers and relays retain core authority over their systems. This chart highlights the silent restore trap. You cannot hit reset if physical hardware is still actuated. It requires a multidiscipline unlock. Closeout is prohibited until authorized owners confirm valves, dampers, and fans are physically restored to safe, normal states. If testing or operations reveal an unexpected result in the matrix, it must go through this management of change workflow. The team must classify the deficiency, apply impairment control, throw logic, and perform a full retest to close the loop. Looking at this final schematic, we see the core takeaways. Verified events bypass timers. IST proves end-to-end physical behavior, and no reset is valid without physical restoration. Life safety and business continuity are only protected when engineering, programming, and operations run on one unified logic set. The deterministic matrix ensures that from the first particle of smoke to the final system reset, absolutely nothing is left to chance.